Welcome to our presentation on Ace Solver, a machine learning-based solution to one of the most challenging games in the world, No Limit Texas Hold'em Poker. Poker is a game that beautifully combines skill, strategy, psychology, and chance. Among its many variants, Texas Hold'em stands out as the most popular and challenging. Players compete not only with the strength of their hands but also by interpreting their opponent's actions, making decisions with incomplete information, and managing risk. And the objective is to maximize the value of your bets over time, either by having the best hand or by convincing others to fold. From a machine learning perspective, poker is particularly interesting because it mirrors many real-world decision-making scenarios. It involves incomplete information, adversarial dynamics, and the need to balance short-term actions with long-term strategies. Additionally, our project doesn't just focus on creating a poker bot. It's designed to bridge the gap between cutting-edge ML and practical player development. And so, by collaborating with the Virginia Poker Club, we've positioned Ace Solver as a tool to help players refine their strategies in a highly competitive environment and become better poker players.
To start breaking down poker, we started by looking at one of the simplest variants, Coon's poker. In this variant, players are given one of three cards, an ace, a king, or a queen. And players are then betting on who has the highest card. There's a $1 ante, and there's a one round of betting where players can either bet $1 or fold. And if a player folds, they forfeit the pot to the other player. If both players bet $1, the $4 pot will go to the player with the higher card. So players want to win by either having the highest card or by getting the other player to fold. And we solved Kuhn's poker and by looking at this tree initially. And this tree is just a diagram of different strategies and how they play out. Over here, we see the jack and the queen. When the jack just folds all the time, they lose $1 because they had a $1 ante. And when the jack bets and the queen folds, they make $1. So the only situation where a jack can win is if they get a queen to fold. Similarly, for a king, which is the highest card in this situation where we have a jack, a queen, and a king must get as much money as possible. So they want to bet and get called by a queen. And we solve this problem using convex optimization. This is just a system where we can take a bunch of constraints, put them to linear programming, and find an optimal point by searching around what's called a convex space. And this is essentially what machine learning tries to do by approximating really large convex spaces. But over here, we're able to reduce a convex space sufficiently so that we can solve it explicitly. And we found that with an ace, you can bet with any probability from 0 to 1. The only contingency is that your queens must bet with a over 3, and your kings must bet with a plus 1 over 3. This is interesting because there's no fixed solution of probabilities, but there's rather a range of probabilities and relationships that exist between the probabilities. And we find that no matter what player one does, as long as they follow this a over 3 and a plus 1 over 3, their EV is 17 over 18 at most, meaning they lose 1/18th of a unit every time they play because there's a $1 forced bet. And the main takeaways is that poker is not just degenerate, and there actually is a lot of math behind it because you must bluff in proportion to how you value bet, and being second to act is always better, and we proved it mathematically here. And then in the next slide, we sort of show like what the strategies look like. So player one and player two each have 64 possible strategies based on the set of cards that they have, which is quite a lot. And solving matrix decide is feasible, but we felt that we could do something more intuitive. So we use logic and pretty definite logic to reduce this to 8 by 8 matrix because we could rule out most of the strategies as infeasible or strategies that is would be long-term losing. So we got to 8 by 8 matrix and then we solved the convex problem and we found the solution on the previous slide. And the interesting thing is in real poker, the actual matrix would be 10 to the power of 20 or more, probably significantly higher for each player. So the matrix would certainly not be solvable by using linear programming, but rather we have to use a lot of abstractions and optimizations to make it solvable. And this is a convex problem setup.
Awesome. So continuing on from Coon's Poker, we have No Limit Texas Hold'em, which is one of the most popular games like we talked about before. The game is played with a standard deck of 52 playing cards and typically involves 2 to 10 players. In our version, it's heads up with 2 players. And briefly, each player is dealt 2 private cards known as whole cards and shares 5 community cards. And the objective is to make the best 5-card hand using any combination of your whole cards. And like Akash mentioned, the game's complexity lies in its immense decision space. So trillions of possible game states make it extremely challenging to model comprehensively, which we solve later.
Right. So this all sort of begs the question, which is how do we actually go about training our AI bot? Recall before that, as with Coon's Poker, we can encode this sort of game state into a tree that we could traverse as we commit to certain actions. Similarly, we could do the same thing with NLH Poker. It's just, as my colleagues have mentioned before, the size of the tree becomes much more expensive, much more huge, and it's just infeasible to compute fully. So what do? We use these ideas called counterfactual regret minimization and Monte Carlo sampling, which is just a way for us to train the AI on what to do at each different decision tree or node. And this relies on the sort of idea of regret. So regret is just if I had done X, I would have made Y more dollars. And so for each action that the bot commits to at any given spot, it has some sort of regret, and its goal is to minimize the regret over time, and by backtracing through different actions and seeing how much more money it would have made if it did X different thing, and so on and so on. And over time, we build a sort of expansive tree network, telling the bot what to do. But before we do this, we have this idea of reducing extractions. As my colleagues have mentioned before, the state of the tree is so expensive for an NLH that it's infeasible to compute or even to run this CFR algorithm as is. So we reduce this, we abstract away by clustering different hands into different buckets that the AI could then act on differently. And to do this sort of abstraction, we use k-means. This is just a hard-coded k-means to classify these buckets in a hard-coded way to that the bot uses as it goes through its 10 hours of iterations. And then we train the AI on a GUI.
And this is just some of the results. So we use the CFR engine that was pre-built, and we heavily modded and changed the engine to be compatible with Texas Hold'em. And over here, we can just see the regret that's being output and what the CFR training loop looks like. So this loop runs 50,000 times, and this does it for 20 epochs, and we can see the regret goes down over time. And again, we borrowed this engine similar to how one would use TensorFlow or Keras. And this is just a picture for GUI. So this GUI is also borrowed. It's like a publicly available GUI that a lot of people use for their heads up bots for No Limit Hold'em. And we can just see a player playing against the bot over here. And then on the right, the bot takes some unconventional lines, such as going all in with King High. And the results versus Lumba, which is the industry standard for Texas Hold'em heads up, is -11 BBs per 100 hands, which we thought is pretty good because the industry best is 19.4, and that tool costs $1,500 a year and costs hundreds of thousands of dollars to train.
Finally, we played our bot versus 10 VPC players in a game that they're pretty familiar with 100 big blinds deep, 1-2 no limit hold'em. Asolver ended up beating 3 out of 10 VPC players over 250 hands, and over 100 hands beat 5 out of 10 players. When the VPC players played together, we actually did end up beating Asolver over a 1,000 hand period. We also trained it versus Coonspoker, which ended up beating 6 out of 10 players with our bot, which seems to make sense. And overall, this sort of indicates that our bot performed relatively optimally, but like we talked about before, still could be improved with A, a larger search space, B, more complexity in training, and C, more compute. So as a quick wrap up, we use reinforcement learning to create a poker bot, Asolver, that optimizes heads up no limit poker. We implemented Asolver using CFR and Monte Carlo search, and reduced the search space of no limit hold'em by sort of abstracting decisions in order to sort of balance compute. Our results allowed VPC players to train against an optimal poker bot, ultimately improving their decision making and risk tolerances. Thank you so much.
Okay, that was a